Very much. Thank you for giving me a chance to present a bit the work for my group at ETH. It's a pleasure to be here to learn about dexterous manipulation, about what people are doing currently in the field, and I will try to show a little bit what our thoughts are and where we are taking our research in this matter. So the talk is called "Giving Robots a Hand," and that's very much going to be the theme throughout this whole talk of like, we are a lab that's building robots, that's building soft robots, that's building rigid robots, but also we are interested in giving them the ability to be autonomous. So why do robots need hands? I believe you all aware of that the traditional robotic gripper can do very structured tasks in very structured environments, like here you see in a factory, you can assemble cars these days. It works really well. But the moment you go into McDonald's, you have an issue because you cannot use the same robots, the same approaches in assembling a burger patty or anything related to these very fine dexterous tasks. And our world in companies is centered around using the human hand for these type of tasks at the moment. So if you look into, let me just move this away here. If you look into what is out there, there's obviously a lot of research has been focused on hands that are less articulated. So two-finger grippers, we just heard about in the previous talks as well. That this is obviously something that has been used a lot for data collection, for policy generation, and for other research in terms of machine learning. But all of these hands are usually task specific and they can do one specific thing and that they're good at. And another issue is in industry, at least, we have a lot of the high setup costs in getting these robots running to do something for you autonomously. So you need an expert, you need a lot of programming set up. So these are the two challenges. On the one side, we have a lot of hands that are not really articulated and dexterous. On the other side, we have the issue of if you want to bring those hands into the real environments, we need machine learning. So if we take inspiration from nature, that gets us into musculoskeletal designs. And that's something that we really like in our lab. We love the idea of musculoskeletal design. So here you see the human hands. And if we were to further analyze it, you see we have all these degrees of freedom in the human hands that can be articulated and can be used, including also the softness that's not even shown in the video, the softness of our skin, the compliance of our muscles, and the whole setup. So what do we need here? We need muscles, we need bones, we need tendons, ligaments, and joints. All of these aspects are crucial to build a robotic hand, or for that matter, any type of robot that's musculoskeletal. So if we look into how to make this happening, I believe there's a path to take that brings together the best of all of the worlds. So we need some soft robotic technologies. We need the ability to bring in soft, deformable structures and actuation methods that are more muscle-like. We need to use the insights that we learned from building rigid robots, robots that have motors and metal encasings or hard structural plastic encasings. And we need to see of how does nature build their hands. And so if we combine this all together, we get this future where we are driving our hands and any type of robot using a musculoskeletal-based design. So we start in this exploration by looking at the hand itself. Not looking at the muscle yet, but just looking at the hand. And we decided to build this hand called the 5-hand. It's a dexterous robotic hand that has in total 11 degrees of freedom in the first iteration. By now, the next and newer versions that we're still working on have more degrees of freedom, but we start off with these 11, where we have a gesture-based control ability for these for the system. We have just heard about it in the previous talk as well. Here we used, in the beginning, we used a leap motion device, and I will show you some other approaches later on of how we're teaching these hands. And in the beginning, we just used servo motors. No muscles yet, just tendon actuation running onto servo motors. With this design, we were able to pick up to 10 kg of payload. The hand itself is about 1 kg. It is very compliant because our motors that we put into this hand are back-drivable, which makes it very interesting for applications that require a little bit of compliance and handling the uncertainty. And we also placed in sensing into the hands. Initially, we first had sensing in the fingertips, and at the moment, we're working on a newer version where we have more sensing integrated. And it gets me to an interesting problem. A lot of the research right now is very much focused on the visuals, on looking at the scene and looking at your hand and looking at the object. But here's a study that was done in Sweden many years ago, where users were asked to pick up matches from a from a matchbox. And imagine you would be trying to do this right now yourself, picking up these matches and trying to lit the match. You're thinking, oh, there's nothing trivial about this. It's super easy. I've done this since I was a little child. But now imagine doing this after you were injected lidocaine, something to anesthetize, like something to numb your fingertips. So your fingertips are numbed. You don't feel what you're touching. The only thing you feel is sort of you see what's going on, and you have some more really coarse proprioception in your hand, maybe from further up the hands. That's all you have. And this lady has a really hard time to light this match. So that means we need tactile feedback, and we need this in a very high resolution. And I assume some of you are obviously already working on this, and this is something that we have to push forward. So we started putting sensorized skins into our hand. Jana, one of the students in my group, she had started looking at this. And this was a collaboration together with NTU in Singapore, where we started looking into, can we bring very many small resistive sensors into our skin? And because we produce everything in our lab, we have also the ability to place these sensors anywhere and to route our electronics in this way. So here the idea was bringing these small sensors into a silicone skin. And then we made this hand that is skin covered and it has these sensors in it, and tried it out in various grasp formations. So far, this was all open loop. There was nothing yet autonomously controlled, but we were trying to use this to just see, can we start discerning different objects that we are grasping? So that's what you see with this k-means clustering, where we cluster the different objects that we picked up, and we're able to see, oh, okay, we can actually discern different objects grasped in different ways. So this is at least a starting point that a machine learning algorithm could eventually use to train with and to put on top as an additional modality besides computer vision. So now, where are we going with this? We're currently looking into making hands here. I've taken the skin off so you can see a little bit more the architecture. We're building finer form architectures where we also include a wrist joint, which we need to actually give this hand the ability to also, when you're trying to do something on the table, you have to be able to use your wrist. The wrist is super crucial for manipulation. And also, we have been improving the motors, while some parts of my team, and we'll get to this in a second, have been looking into using muscles. We also have been trying different sensing modalities to bring in and trying to bring the sensing lines into this, which is really challenging, as you can imagine. So if you start introducing various types of sensing modalities, such as IMUs, magnetic sensors, capacitive sensors, piezoresistor sensors, how do you put all of the sensing into the fingertip without hindering the mobility of your joints? And then we've been looking into building the soft robotic tissues on there. So how can we make a nice soft fingertip, a nice soft finger element in between, so that we really can produce hands quickly and also provide them to the community if you want to do research with this without having to put a lot of investments into these hands. We are aiming here for making hands that cost on the orders of thousands, not tens of thousands or more, while you have the ability to get the sensing. In the end, another really important problem with our design is we're using this rolling contact joint design, which is inspired by nature. So if you think about your hands, you have two bones that go on top of each other with some capsules around it. We're not using pin joints, but in order to do this reliably and run these hands for a long time, we need to have a way of having the ligaments that are holding it together be retensionable and they remain tensioned. So we're looking a lot into this design of how can we make these ligaments tension, so these cross ligaments hold the fingers together. Ronan is the person in my group that's currently leading this effort, and it's extremely interesting. It's a lot of fun. If you want to come visit us, please come by. I'm happy to show you around. So it's still quite tedious to make these hands and to assemble them and to do all of the routing. So we're trying to find ways of making this simpler and also therefore lowering the cost of this. But we have parallel efforts where we're just asking ourselves, can we just 3D print a whole hand in one shot? Instead of basically having to go through the challenge of making a hand that's assembled, could we print all of it at once? So here, that's where we're looking into something called vision-controlled shedding. Thomas in my group has been working on this, and here we basically use the inkjet method where we deposit layers of inkjet material, millions of droplets at a time, and we're getting rid of what you see here in the middle as the mechanical scraper. So think of a Stratasys Connex printer, but instead of having a scraper, we use a vision system that scans the layer bit by bit. And so we can scan every layer that we print, and therefore we can use a different material chemistry for producing these hands. So you print, you droplets down, you shine the UV light on it, you scan, and you see the unevenness. And then the next layer that you print, you correct for that unevenness, and you don't need to mechanically scrape every single layer. And this is how we're producing these robotic hands. Here you see a hand that comes out of the printer. It's surrounded by wax. That's what is the support material. And you remove the wax afterwards to make the hand. So here is the starting point. You have initially a design that you made. This was a scan of a human hand. We additionally designed the tendons and the capsules around the scan from this human hand. And then we slice it up into layers. And then we use our feedback control approach to actually produce this hand layer by layer and correcting at each single step of the print process. So in the end, we have printed all of it, the tendon guides, the sensor pads, the reinforced tendons, all of it is designed. It is a mix of soft and rigid thiolene material. And we produce the hand as you see it here in a single shot. And then for this particular study, initially we just put motors at the ends that allowed us to basically show the hands. And let me just skip forward a bit, show why it's so slow. So here is one of the dexterity tests. So this is pulling on the 3D printed tendons. And then we also have introduced a palm sensor into the hand where we can detect the sensing. The challenges that we had still is we could print it, we could actuate it, it was able to sustain the forces, but it was not super fast and we couldn't quite have it at the robustness that we wanted to have it at. So one of the next things that we did is we introduced McKibben muscles into the hand. Instead of using motors, we have muscles at the bottom that pull at it and allow it to be articulated. And with this, we were able to make a hand that had muscles instead of using motors. But what we're not showing here is that all of driving these muscles requires a whole other infrastructure of pressure, compressed chamber, compressed air, and valving and so forth exterior to this. So it's not really a solution that you can put directly onto your robot arm. So we are pushing in our lab towards the direction of getting rid of motors and wanting to go towards using systems that don't have any more electromagnetic motor in the joints. Here's an example of a leg, and putting muscles into the structures. So instead of having a motor, you would have pairs of muscles, which are electrically driven. These are Hazel muscles. So we have multiple of these. They are also self-sensing. You can sense your capacitance. And then you basically don't use an electromagnetic motor that rotates around with a magnetic principle, but you use electrostatic forces. So you have attractive forces where you apply voltages to these muscles and then they contract. You can replace the joint angle encoders with the capacitor sensing on the muscle. And you replace the transmissions of these systems, which you would previously have in your gearbox, with the nonlinear moment arms of where your tendons are attaching to in your design. So here is an example. This is not a hand yet. Yes, I agree. This is just a jumping robot, but it's something where we try to put 4 packs of these muscles together to allow these robots to act. This is about the size of a robot. And we started building a single leg. And this is eventually going to be something we also want to further develop to be able to miniaturize it and put it into our robotic hands. So, but with this, you might wonder, okay, so you have shown us this design, but now what's the deal with actually making these things autonomous? Because yes, we can use these hands, we can pick up objects, but we cannot do this yet purely with computer vision or even with integrated sensing. So how do we get to this point? And we already heard talks earlier today that are doing really important work in this direction. And I think this is going to be really the collaboration of multiple groups here will bring it all together to make it happen. One of the quotes that I recently saw was from a novelist. She writes fantasy novels and other books. And she was saying, I want AI to do my laundry and dishes so that I can do the art and the writing. Not for AI to do my art and writing so that I can do my laundry and the dishes. And I think it's a very valid point. We have very good tools right now that can do the writing for me, that can make nice images and all of these things. But really, we would love to keep doing those things potentially as humans, being creative, and instead move towards actually having these robots do the autonomy. So how can we make these robots autonomous? We can use reinforcement learning techniques, or we can also use imitation learning techniques. And you are hopefully familiar with these techniques in principle. But I will show you now 2 of the approaches we've been working on One of them is on the reinforcement learning side, the other one is on the imitation learning side. So this is on the reinforcement learning side, where we took our 5-hand and we basically taught it in simulation of how to learn how to rotate this ball in hand. So that it has a policy that you can trigger to go forward rotation, backward rotation, and actually spin the ball around as you like it to do. This is the work that Yasu has been doing in my group. So we run it, here's 8,192 robot hands in iSection, where we train it. We use domain randomization. We use this GPU-based simulators in iSection. It's super handy to use it for our hands. And we then basically taught it how we can do this reorientation of the hands. In this case, the basics are the basics underlying to this is PPO, what we are using, but here is just a simplified version of RL, which is, you're probably familiar with this. You have a reward in the state that goes to your algorithm and it predicts an action with its policy. And in our case, we want to maximize the discounted cumulative reward that we are using in this case. And in the end, we get an estimate for the policy gradient that we are using to update the parameters theta of our policy that we use to run using gradient ascent. So here we can update our theta, our weights of our MLP. And with this, we can train the reinforcement learning agents. And here is what we do in the first step. On the left side, you see that we first train the reinforcement learning policy in simulation. We train both a critic MLP and an actor MLP. The critic MLP has obviously particularly good access in simulation to all of the things we won't have access to in the real world. And then we roll out our actor MLP that was trained in simulation and apply this to our robotic hand example. We had a lot of fun with this because we also brought this hand to a talk in India, and we did some on-stage live demo. It was pretty stressful for us to make this happen, but it worked fine, and it was actually interesting how well we could actually bring this out and move it around the world and still get it to do this manipulation example. So what did we need to do to overcome the simulation gap? We obviously used techniques that are known from literature, such as domain randomization, so we can actually apply what we have in simulation to the real robots. So we could then, with the domain randomization, actually, as you can see here in this example, let me run this again, achieve proper forward rotation, while without this, we were never able to achieve the rotation. Another thing that we did here, and this is obviously part of the training process, you see this like clear sphere here. So we didn't want to use external vision. The only thing we use is we put an IMU into the sphere for training data collection, and also to reward our algorithm on the actual robot. So now, another thing that we started doing is, in order to kick off going away from reinforcement learning and more from human learning, we also are interested in seeing what the community has been doing in terms of imitation learning. So we're using teleoperation to do data collection. One of the first ones was using a leap motion device. You see the video down in the bottom left. That's basically moving my hand around. The leap motion finds my skeletal model, and then we apply this to the hands. We took a step further, and we're now using these motion capture gloves that allow us to, here is Davide doing the manipulation, allowing us to manipulate with our 5 hands and placing things into, for example, here, put the bottle into the cup. And this is obviously a way of how you can teach them. It's not a way to scale it really fast, but at least allows us to do interesting, fun demonstrations and kick things around. So one of the works that Elvis is doing, Elvis is another PhD student in this area, is working on DexFormer, one of the imitation learning approaches. So here we're just taking, with just our proprioception, quote unquote, is just 3 visual feeds from the top. You see these 3 video feeds, one from the top, one from sort of isometric, and one from the hand, from the wrist. And then we have a vision encoder that goes into a transformer model, and that allows us to do robotic actions on our 5 hands. And we have started initially with using the ACK architecture that was introduced from the team around Aloha, and they had done a really nice job using this latent style variable C. That was what we started off with. And now we are using a variational autoencoder in ACT, as we're seeing this as a somewhat unnatural thing to use. So what we're proposing with our setup is we're saying, instead of using this like fully masked or future mask, we are doing a random masking, and we're trying to work with the masking on the transformer sides to get a better result. And this is a work in progress at the moment that Elvis is working on. And we hope that with this, we can afford getting faster learning from a few imitations from the human. So initially, when you just do this on the Aloha simulation, this approach, and we're comparing just the vanilla act to our DEXformer and to our DEXformer with full masking, which is sort of like the adjusted act architecture with some other tweaks plus the full masking. The best results we get if we do a random masking of the future steps in the transformer architecture. So I guess that's one of the takeaways from using basing our work on top of act. So here is a result where we take the hand using this DEXformer architecture. It just was shown a couple of demonstrations of picking up the octopus and placing it into the container. And now it's trying to do this. And the human is messing. Elvis is messing with the robot, telling it, no, don't put there, and it keeps going at it. There, the fingertip fell off for a moment, and it keeps going at it, trying to get the octopus and trying to place it. And we've also tried other things where we're trying to do rollouts where we wanted to sort a couple of different cubes. And I think at the moment, we not really have a problem with getting the machine learning architectures in place. I think initially the biggest challenges for my students was, because I'm working a lot with data scientists, is to just learn how to do a fast real-time control on these hands. So really the good old robotics basics of getting a Cartesian controller properly running in real time. So that's what we have now fixed at this point, and we will hopefully soon be able to publish some work in this effort around what Elvis is doing. Another work from Davide, he recently joined my group as a PhD student. He's also working on this direction. He's been trying to look into, can we build up latent space predictions for imitation learning? And particularly is interested, so he looks at the different architectures that exist there for learning from human grasping. And then they usually go into a fingertip inverse kinematics retargeter. And what he's looking into is, can we use an encoder to take these learnings, so it's probably a little bit fade on the left, and put them into a latent space, learn this latent space, and then later on decode it back again and use this latent space as a way of smoothing out all of these recordings and finding one common latent space that we can use for it. So basically, we have the past robot states, the object states, we put them into a transformer model. That transformer model outputs something in our latent space that we have trained previously with all of the training data. So here we're just rolling it out. We're decoding what we are learning in the latent space, and then we're running it on the hands. And so we can now do action space predictions. And when you see action space predictions, they're extremely shaky and they fail. But with our latent space predictions, we get more robust manipulation behaviors. And we showed this both here in simulation. And he's also working on making this happen on the real hands. So to summarize, to wrap it up, what's next? We want to make better hands. We're looking into the hand designs. We're really open to what to do here. Does it have to be a rolling contact joint or other designs? What are the advantages of these? Do we use also a higher degree of freedom joints, not just rolling around 1 degree, but maybe also sort of cup joints that allow us to have more complex motions? Introducing sensing our hands so we can do better proprioception. You see down there in simulation, we get a very different curl than what we're actually having because we are holding up the hands and we're blocking them with the Coke bottle. And how can we integrate muscles into our hands eventually? And one of the major things to then go in the forward is to make them more intelligent. We obviously want to be more robust, and we also want to include tactile information, bringing really dense tactile information sensing. Here, this is, for example, one of the sensors produced by a group at ETH, where we are able to put them directly on our fingertips. That gives us 144 capacitive readouts. So we can read out the fingertips with these 144 sensor readouts. And with this, I would like to say thank you to my group. We just came back from a lab retreat last week. Amazing. If you have a group, you should definitely go on lab retreats. It's the best excuse to use work time to go and hike in the mountains. And really have a good team building experience. And also here just to show you how my group is set up. We have people working on the bio-hybrid robotic side, so building real muscles from cells. We have people building the electrohydraulic muscles, and we have a team of people that just look into machine learning for manipulation and for modeling. And I would love to show also briefly our funding sources. And with this, I just want to mention we have a startup called Mimic that recently started off trying to commercialize these efforts into 3 areas: bakery, glassware handling, and coffee making. And if you want to hear more about this, happy to talk about this, what the team is doing. And with this, I'm open for questions. Thank you very much.
Hello, my name is Katzschmann from National University of Singapore. First of all, thank you very much. It was awesome.
Thank
And
you.
I have a practical question. So I had a chance to work with Shadowhand and the ICAP from IIT.
Yeah.
In both cases, the crucial problem of attendance keep breaking or turning off, and when you want to train it in the workshop, we repair it. So to tackle this, what do you do with these challenges? Thank you.
Okay, so to tackle the challenge of how do we deal with tendon rippage. So I'm working with someone who comes originally from the sort of fine MEMS technology area and also worked in making watches. And so there is a lot you can learn about how to do tendons well and how to route them well to avoid the issue of breaking, because you don't want them to break in the first place. And also you would like them to not age as fast as you might have observed it. So that being said, we're running in the lab a lot of studies where we just keep running them for tens and hundreds of thousands of cycles to see how they age, and then we find the failure points. This allows us to adjust everything on the fly, and because we're building it from scratch, we can adjust these things from scratch. We're obviously pushing this to a point where we are happy for it to do research with this, and the company will have to figure out how to do it more reliably. So the answer is it's a hard problem. It requires good mechanical engineering, and I don't think the answer is to just build 3-fingered hands instead of 5-fingered hands.